Hello everyone. So today we're going to be talking about acids and bases. These are some important terms to know. This blank slide is just for you to add your own notes if you are taking notes on the slides. So let's talk about what are acids and bases. This is a video comparing and contrasting the properties of acids and bases right here. You should know that acids are generally positive and represented by H plus or H3O plus, and that bases are generally negative and represented by OH minus. If you are in my Gen Chem class, you will be doing this homework assignment using the video from the previous slide to create a Venn diagram comparing and contrasting acids and bases. So I want you to talk about the properties of acids and bases and comparing and contrasting them. So now we're going to talk about the autoionization of water. Here we have two water molecules that break apart into H3 plus, or a hydronium ion, and OH minus, also known as a hydroxide ion. We'll be talking a lot about the autoionization of water because pure water is considered to be the standard for a neutral substance. So take a moment. We've practiced equilibrium expressions before, and write out the Kc expression for the autoionization of water. Alright, I'm assuming you've tried it. The Kc expression for the autoionization of water is the hydronium ion to the first power and the hydroxide ion to the first power, which of course you don't need to write the first power. We do not include the two water molecules in the equilibrium expression because they are pure liquids. You should also know that this expression is referred to as Kw, so it has a C here, but this particular expression is referred to as Kw. And the Kw is indicative of, specifically, this is the autoionization of water equilibrium expression. This Kc expression is equal to 1.0 times 10 to the negative 14th. So when we look at this, let's think about whether or not does the equilibrium for the autoionization of water lie to the left or to the right of the equation. To the left, because Kw is less than 1 and is very small. When we have a small Kw, that is indicative of more reactants than products. Okay. So remember the Kw expression is products over reactants, and so if you have a very, very small Kw, that means that denominator is a whole lot bigger than the numerator, and the denominator is made of reactants. Okay. So given the Kw expression we just talked about, calculate the concentration of the hydroxide and the hydronium ions at equilibrium. I'm assuming you have attempted the problem. Note that the question asked for a concentration at equilibrium. We were given a Kc expression and you have two unknowns because it asked you for the concentration of the hydronium and the concentration of the hydroxide ions. So because we have two unknowns, we can't just plug it in and solve for 1x. We are using a shortened version of the ICE table. Okay. So when you have two unknowns, that is indicative of using an ICE table. Here I didn't write the initial change in equilibrium because we don't have an initial, which we don't really need one because if you look back at the chemical equation, the mole-to-mole ratio of hydronium to hydroxide is 1 to 1. And so, excuse me, it's just asking you for these concentrations. And these concentrations will be the same because of the 1 to 1 ratio, so we'll represent both of those by x. And we will set it equal to the Kc expression. Then we have x squared equals 1.0 times 10 to the negative 4th. When we take the square root of both sides, you will have 1.0 times 10 to the negative 7th. And that is the concentration of hydronium and of hydroxide. So to recap a bit, acids are generally positive and represented by H plus or H3O plus. Bases are generally negative and represented by OH minus. We will be doing calculations with concentrations of H plus or H3O plus and OH minus. So why is it that H plus and H3O plus can be used interchangeably to represent acids? Both H plus and H3O plus represent what can happen during the autoionization of water. Notice that H3O plus is the product of the autoionization of two molecules of water, and H plus is the product of the autoionization of one water molecule. Because both of these products represent the autoionization of water, this is why H3O plus and H plus are used interchangeably to represent acids. Here we're using concentrations of hydroxide and hydronium to define acids and bases. When a solution contains more hydronium or H plus ions than hydroxide ions, then the solution is considered acidic. When the concentration of hydronium and hydroxide are equal, the solution is considered neutral. When the concentration of hydroxide is greater than the concentration of hydronium, the solution is considered basic or alkaline. Note that the Kw expression for water is the same regardless of the pH of the solution as long as the solution stays at 25 degrees. Recall that Kc, or in this case Kw, expressions can change if the temperature changes. There are different types of acids and bases. Generally speaking, acids either give away positive or accept negative charges in the form of an electron pair. So when it accepts a negative charge, it'll be accepting an electron pair. Bases usually donate negative charges by donating either a hydroxide or an electron pair, so OH minus donor, electron pair donor, or it accepts positive charges. Okay. These definitions will come back to haunt you in future chemistry classes. But if you don't remember anything else about acids and bases, remember that acids are generally positive, that's why they can give away H+. And they are positive, they can accept negative because like attracts. Bases are generally negative, that's why they can donate OH groups or an electron pair. And because they are negative, they can accept positive because like positives are attracted to negatives. This slide just illustrates that the Kc expression for water is denoted as Kw. So this is just emphasizing that if it says Kw, it's not anything strange, it's just a special Kc expression. And this should say at 25 degrees Celsius. Because again, the temperature can cause this to change, as we will talk about in just a second. But first, let's calculate the concentration of OH minus when H3O plus is 4.0, concentration is 4.0 times 10 to the negative 6 at 25 degrees Celsius. So these are your givens. And so I'm going to give you a second, pause the video, and try it. Alright, I'm assuming you've tried it. You should note that how many unknowns you have. You only have one unknown, okay? Because you have this expression here, the Kw expression, and you have the concentration of hydronium. You can plug in your concentration of hydronium into that equation and then just solve for your OH minus. That's how you know you don't need an ice table here, because you only have one unknown. And so when you plug that in, you should get 2.5 times 10 to the negative 9th. For the problem we just solved, is the solution acidic or basic? Well, the H3O plus concentration is greater than the OH minus concentration, making the solution acidic. So let's take a look at a case where temperature increases. These values listed are your givens. We can see that an increase in temperature causes an increase in kW. So this is our question. Is this an endothermic or exothermic reaction? So we can see as kW increases, or as temperature increases rather, kW increases. An increase in kW indicates an increase in product. So if we have an increase in product, if the amount of products has increased, then which way has the reaction shifted? The reaction has shifted to the right to make more product. And if the reaction has shifted to the right to relieve stress, right? Because Le Chatelier's principle says we shift to the right to relieve stress, then the original stress must have been in the left where the reactants are. So if the original stress was in the left, heat had to go into the reaction. And if heat had to go into reaction, that makes the reaction endothermic. Okay? This was a conceptual practice of Le Chatelier's principle. Another practice problem. Calculate the concentration of OH and H0 plus at equilibrium at 50 degrees Celsius. So take a moment and try it. Right, I'm assuming you've tried it. You have to calculate two unknown concentrations. So here you're going to be using that simplified ice table that we used before. Right. Since you have a 1-to-1 ratio, it's going to be very similar to before. You're going to have x times x, giving you x squared. X squared equals 5.5 times 10 to the negative 14th. This was given to you in the last slide. And then you take the square root of both sides. And your x should be 2.3 times 10 to the negative 7th when you use significant figures. Okay. So is the solution we just solved for acidic or basic? Right. It is neutral because the hydronium and hydroxide concentrations are equal. This X represents both the concentrations of hydronium and hydroxide, right? Because they are the same because of that 1-to-1 ratio. So this solution is neutral because the concentration of hydronium and the concentration of hydroxide ions are equal. All right, let's talk about the pH scale. The pH scale exists because it is more convenient to work with whole numbers than it is to work with numbers that are very small, like 1.0 times 10 to the negative 14th. Or in this case, on the slide it's written 1.0 times 10 to the negative 7th. Now this is a formula you're going to need to know. This is how they come up with the numbers on the pH scale. The pH is the negative log of H3O plus, or H plus. So let's take a moment and calculate the excuse me, and calculate the concentration, calculate the pH of pure water. So take a moment and try it. Alright, I am assuming that you have tried it. And you will just plug that, you will take the negative log of that number, so you'll need your calculator. And you should get 7. Now you should note that there are 2 decimal places after 7.00, even though there are only 2 significant figures in 1.0 times 10 to the negative 7th in your problem. This is because in a logarithm, only the numbers after the decimal are significant. So when you take the logarithm, only the numbers after the decimal will be significant. I will indicate on the test question whether or not you need to use the rule for significant figures of logarithms. So you still need to know the rule, right? I'm not going to list on the test what the rule specifically is, but I will say use the rule for significant figures of logarithms, as you can see in the example below. Right. The concentration of OH ions in a cleaning solution is 2.0 times 10 to the negative 3 molar. Knowing that H3O plus times OH minus equals 1.0 times 10 to the negative 14th at 25 degrees Celsius, calculate the pH. So we know that we can use H3O plus to calculate pH, but how do we solve for pH when given OH minus? Well, we need to figure out how to go from OH minus to H3O plus, because then once we get to H3O plus, we can take the negative log of H3O plus to get the pH, right? So we can use this formula to calculate H3O plus. We have the concentration of OH minus, so we will plug that in here, and our unknown would be H3O plus. And so when you plug that in, you should get 5.0 times 10 to the negative 12th as your H3O plus concentration. Now that we have the H3O plus concentration, how do we calculate pH? You will plug that in into your pH equals the negative log of H3O plus equation, and then you should get 11.30. Remember that only the places after the decimal count as significant figures with logarithms. Okay. So talking more about the pH scale itself, the pH scale normally goes from 0 to 14. It is possible to go below 0 and above 14, but we won't be doing that in this class. 7 is neutral, below 7 is acidic, above 7 is basic. Because this is this is a base 10 scale. So in other words, pH 6 is 10 times more acidic than pH 7. Even though it's only one number away, it's 10 times more acidic. So milk is 10 times more acidic than pure water. So, knowing that, true or false? Is pH 5 100 times more acidic than pH 7? This is true because it is a base 10 scale. So from 5 to 6 is 10 times more acidic, from 5 to 7 is 100 times more acidic. If we were to compare, for example, the acidity of black coffee and an egg, you'd have 10, 100, 1000. So black coffee is 1,000 times more acidic than an egg. So even stuff in everyday life that you deal with every day, that has a great difference in acidity based upon the pH scale. These are some other formulas for you to know. The pH, just like the pH is the negative log of H3O plus, the pOH is the negative log of OH minus. pKw equals the negative log of Kw at 25 degrees Celsius. As you already know, pH is the negative log of H3O plus. Now, when you take this equation that you already know, and you take the log of both sides, you will get to this equation, pH plus pOH equals pKw. In other words, at 25 degrees Celsius, pH plus pOH equals 14 at 25 degrees Celsius. Okay, so these are formulas that you need to know. As usual, I suggest you make a formula sheet. You should know that doing the opposite of a log means doing 10 to the power of a log. Okay, you'll be needing to do that in future questions. So slides 37 through 39 contain some practice problems for you to go through. Right. Feel free to email me if you have any questions.